What specific problem does the proposed visualization of thought, VOT, prompting method aim to solve in the context of large language models, LLMs, and spatial reasoning tasks?
The proposed visualization of thought, VOT, prompting method aims to solve the problem of enhancing spatial reasoning capabilities in large language models, LLMs, by eliciting the mind's eye of LLMs for visualizing their internal states during reasoning steps in spatial reasoning tasks. VOT prompts LLMs to create and manipulate mental images in their mind's eye, similar to how humans use mental imagery for spatial awareness and decision-making. By incorporating a visual spatial sketchpad to visualize reasoning steps, VOT helps LLMs ground their reasoning in visual representations, leading to improved spatial reasoning performance. This method addresses the limitation of LLMs relying solely on language to reason about spatial information, expanding their cognitive abilities beyond verbal reasoning. VOT enables LLMs to generate reasoning traces and visualizations in an interleaved manner, enhancing their spatial understanding and facilitating multi-hop spatial reasoning tasks. Ultimately, VOT aims to bridge the gap between LLMs' linguistic capabilities and their spatial reasoning skills by leveraging mental imagery to guide reasoning steps and improve performance on spatial tasks.
How does the proposed method, visualization of thought, VOT prompting, work in enhancing spatial reasoning in LLMs? Illustrate step by step.
The proposed method, visualization of thought, VOT, prompting, enhances spatial reasoning in large language models, LLMs, by eliciting their ability to create and manipulate mental images in the mind's eye for spatial reasoning. The process involves several steps. 1. Prompting. LLMs are prompted with the instruction, visualize the state after each reasoning step. This prompts the models to create mental images of their intermediate reasoning steps. 2. Interleaved reasoning traces and visualizations. VOT introduces a visual spatial sketchpad to each thought generated by the LLM. This allows for the creation of reasoning traces and visualizations in an interleaved manner. 3. Visual state tracking. The concept of a visual state is introduced, representing a partial solution at each step of the reasoning process. This includes the input, sequence of thoughts, and sequence of visualizations up to that point. 4. Derivation of subsequent states. The visual state tracking sequence guides the derivation of subsequent states in a grounded context, reflecting spatiotemporal causality and enhancing the spatial reasoning capabilities of LLMs. 5. Evaluation of spatial understanding. The accuracy of spatial understanding is measured by the proportion of correct answers when the visualization aligns with the corresponding state. This ensures that LLMs make correct decisions based on accurate visualizations of their internal states. 6. Comparison with other prompting methods. VOT prompting is compared with other methods to analyze how visual state tracking behaviors differ among prompting techniques. It is observed that VOT significantly increases the visual tracking rate by explicitly prompting LLMs to visualize their reasoning traces. 7. Enhancing final answers. The accurate visualization of internal states is crucial for LLMs to make correct decisions. VOT aims to generate accurate visualizations at each step to improve the groundedness of the models and enhance their spatial reasoning capabilities. In summary, VOT prompting works by guiding LLMs to create and track mental images of their reasoning steps, enabling them to visualize their internal states and make informed decisions based on spatial understanding and manipulation.
What are the theoretical or practical benefits of using the visualization of thought, VOT, prompting method compared to other prompting techniques and spatial reasoning tasks for LLMs?
The theoretical and practical benefits of using the visualization of thought, VOT, prompting method compared to other prompting techniques in spatial reasoning tasks for LLMs are significant. The VOT prompting method enhances LLM's spatial reasoning capabilities by eliciting the mind's eye of LLMs to create and manipulate mental images for visualizing their internal states and informing subsequent reasoning steps. This method allows LLMs to visually interpret their actions within a grounded world, leading to improved performance in spatial reasoning tasks. The VOT prompting method enables LLMs with visual state tracking, which enhances their ability to generate reasoning traces and visualizations in an interleaved manner. This approach boosts the effectiveness of LLMs in understanding and manipulating spatial information during tasks like navigation and tiling. Additionally, VOT prompting increases the visual tracking rate noticeably by explicitly prompting LLMs to visualize their reasoning traces, thereby improving their spatial reasoning performance. The VOT method also helps LLMs in generating accurate visualizations at each step, which in turn enhances their spatial understanding capability and contributes to significant performance gains in spatial reasoning tasks. Overall, the VOT prompting method provides a structured and effective way for LLMs to leverage mental imagery and enhance their spatial reasoning abilities, making it a valuable technique for improving LLM performance in spatial tasks.
How were the effectiveness and performance of the VOT prompting method validated in the study?
The effectiveness and performance of the VOT prompting method were validated in the study through empirical evaluations on 3 tasks: natural language navigation, visual navigation, and visual tiling. The study compared different models, GPT-4, GPT-4v, and prompting techniques across these tasks. The findings consistently showed that the VOT prompting induced LLMs to visualize their reasoning steps and inform subsequent steps, leading to significant performance improvements on the corresponding tasks. The study also introduced a metric to evaluate the spatial awareness and spatial reasoning abilities of LLMs, including metrics such as average completing rate and success rate for route planning tasks. The results demonstrated that GPT-4 VOT significantly outperformed other settings in all tasks across all metrics, showcasing the effectiveness of visual state tracking in enhancing spatial reasoning capabilities. Additionally, the study provided qualitative comparisons between outputs of VOT and COT prompting methods, showcasing the differences in visual state tracking behaviors among prompting methods and how visualizations enhanced final answers. Overall, the study's validation of the VOT prompting method was based on quantitative and qualitative analyses, demonstrating its effectiveness in improving LLMs' spatial reasoning abilities.
What specific results were achieved with the VOT prompting method in the natural language navigation, visual navigation, and visual tiling tasks?
The VOT prompting method achieved significant performance improvements in the natural language navigation, visual navigation, and visual tiling tasks. In the natural language navigation task, GPT-4 VOT outperformed GPT-4 with OVIS by 27%. In the visual tasks, GPT-4 VOT significantly outperformed other settings in all tasks across all metrics. The performance gap between GPT-4 VOT and GPT-4v COT in the visual tasks demonstrated the effectiveness of visual state tracking in enhancing LLM's spatial reasoning capabilities. Additionally, the VOT prompting method showed promising results in the visual tiling task, where LLMs had to comprehend, organize, and reason with shapes in a confined area. The VOT prompting method enabled LLMs to visually interpret their actions within a grounded world, leading to improved performance in spatial reasoning tasks.
What are the limitations or drawbacks of the visualization of thought, VOT, prompting method based on the findings presented in the paper?
The limitations or drawbacks of the visualization of thought, VOT, prompting method based on the findings presented in the paper include the following. 1. Inconsistency between language and visualization. The paper notes that there is a common observation of inconsistencies between the language instructions generated by LLMs and the visualizations produced. This discrepancy indicates a limitation in the spatial understanding of the models, which can lead to incorrect visualizations even when the language instructions are accurate. 2. Limited visualization capability. The LLMs may struggle with accurately visualizing the internal states, which can result in suboptimal visualizations. This limitation can hinder the effectiveness of the VOT prompting method in enhancing spatial reasoning capabilities. 3. Self-refine mechanism. While LLMs may refine their reasoning based on inaccurate visualizations, the need for such self-correction suggests that the initial visualizations may not always align with the correct spatial understanding. This self-refinement process indicates a potential drawback in the initial visualization accuracy of the models. 4. Performance in tasks without visualizations. The paper mentions that in tasks where LLMs can leverage logical reasoning without visualizing their internal states, the VOT prompting method might underperform. This suggests that the effectiveness of VOT prompting may vary depending on the task requirements and the model's ability to benefit from visualizations. 5. Performance drop in complex tasks. The paper highlights that the performance of LLMs using VOT prompting drops significantly in more challenging tasks, such as route planning. This limitation indicates that the VOT method may struggle to consistently enhance spatial reasoning in highly complex scenarios. Overall, while the VOT prompting method shows promise in improving spatial reasoning capabilities of LLMs, the identified limitations underscore the need for further refinement and optimization to enhance the effectiveness of the approach across a wider range of tasks and scenarios.
What future work suggestions do the authors make based on the limitations and findings of the VOT prompting method in the study?
Based on the limitations and findings of the VOT prompting method in the study, the authors suggest several future work directions. Firstly, they propose the need for significant enhancements to LLMs to improve their spatial visualization and spatial understanding capabilities. This includes refining the accuracy of state visualizations and ensuring that the manipulation of mental images aligns with spatial constraints. Secondly, the authors recommend exploring how visualizations can enhance final answers in tasks where LLMs can leverage logical reasoning without visualizing their internal states. This involves investigating the balance between visualizations and logical reasoning to optimize performance. Additionally, they suggest further analyzing the differences in visual state tracking behaviors among prompting methods to understand how prompts impact LLM's spatial reasoning processes. Furthermore, the authors propose delving into the origins of the emergent ability of LLMs to visualize their internal states, possibly stemming from tasks involving tabular data, city grid navigation, and maze exploration during code pre-training. Lastly, they recommend conducting more case studies to uncover diverse visualization formats, inconsistencies between language and visualization, and self-refinement mechanisms in LLMs during spatial reasoning tasks.
How do the authors propose to elicit the spatial awareness of LLMs and ground their reasoning by visualizing their intermediate reasoning steps with the VOT prompting method?
The authors propose to elicit the spatial awareness of large language models, LLMs, and ground their reasoning by visualizing their intermediate reasoning steps through the visualization of thought, VOT prompting method. VOT prompts LLMs with the instruction, visualize the state after each reasoning step, which aims to generate reasoning traces and visualizations in an interleaved manner. This method enhances the spatial reasoning capabilities of LLMs by adding a visual spatial sketchpad to each thought during reasoning. The VOT prompting enables LLMs to create mental images of their internal states and inform subsequent reasoning steps by visualizing their intermediate steps. This process involves generating visualizations in text form to represent the internal state of the LLM at each reasoning step, allowing for the derivation of subsequent states based on spatiotemporal causality. The visual state tracking sequence is implemented by creating mental images of the internal state after each reasoning step, such as marking a path on a navigation map or filling a rectangle in a tiling task. By visually interpreting their actions within a grounded world, LLMs can enhance their spatial reasoning and improve their performance on spatial tasks.
Can you explain the differences in visual state tracking behaviors among different prompting methods, such as GPT-4 VOT, GPT-4 COT, and GPT-4 with OVIZ, as discussed in the paper?
The paper discusses the differences in visual state tracking behaviors among different prompting methods, namely GPT-4-VOT, GPT-4-COT, and GPT-4 with OVIZ. In the experiments conducted, it was observed that GPT-4-COT exhibited noticeable tracking rates across tasks, except in the route planning task. This suggests that LLMs inherently possess the capability of visual state tracking when spatiotemporal simulation is required for reasoning. On the other hand, GPT-4-VOT significantly increased the visual tracking rate by explicitly prompting LLMs to visualize their reasoning traces, leading to improved performance. The visual state tracking behavior was found to be sensitive to prompts, with VOT prompting enhancing the visual tracking rate noticeably. Removing the reasoning prompt from VOT resulted in visualizations being sampled after the model generated the wrong answer, indicating the importance of explicit visualization prompts. The paper suggests that the ability for visual state tracking may stem from tasks involving understanding and manipulating objects in a 2D square grid, as well as exposure to ASCII art comments during LLM's code pre-training, which enhances spatial visualization ability and spatiotemporal causality. Overall, GPT-4-VOT outperformed other settings in all tasks, demonstrating the effectiveness of visual state tracking in enhancing spatial reasoning capabilities of LLMs.
How do visualizations enhance the final answers in tasks such as visual navigation and polyomino tiling, as explained in the paper?
Visualizations enhance the final answers in tasks such as visual navigation and polyomino tiling by providing a spatial understanding and visualization capability to LLMs. In the context of visual navigation, the LLM generates accurate visualizations of the map as it completes each navigation instruction, ensuring compliance with spatial constraints and accuracy in aligning with the corresponding state. This spatial visualization capability allows the LLM to make correct decisions based on the visualized internal state, improving groundedness and contributing to significant performance gains. Additionally, the accuracy of spatial understanding in these tasks is relatively high, above 65%, indicating that LLMs can effectively interpret and reason with the visualized internal states to arrive at correct answers. Despite suboptimal accuracy in state visualization, LLMs demonstrate promising capabilities in multi-hop visualization that adhere to spatial constraints, showcasing their potential in spatial reasoning tasks.